Okay, aloha everybody. So today we're going to talk about population ecology. We're going to talk specifically about how populations grow. So our learning outcomes for the day are to understand how populations grow under idealized conditions, identify and describe factors that limit population growth, describe the effect of limiting factors on population growth, and you should be able to calculate growth rates and predict future population sizes from starting population sizes and given growth rates. And you should be able to do this using both exponential and logistic growth equations. So I want you guys to take a minute and talk now about what factors determine changes in population size. Okay? Think about there's only four things that can actually influence how big a population is. And if we're thinking about a population as a group of individuals within a species in a given place at a given time, what four things can influence population size, can change population size? Go ahead and take a minute to talk about that with your neighbor, and I will wait. Da, 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 da. Pause the video if you need. Okay, so hopefully you've all come up with some ideas. And some of you might have been thinking about things like, oh, resource availability, what quality, how good the habitat is, etc. So that's not exactly what we're looking for. What we're thinking about here are things that can actually fundamental processes that can actually change the number of individuals in a population, change our n, our population size. And for that, there's only two things that can increase our n. That's births and immigrants, so individuals coming into our population from outside. And then the only two things that can decrease our population size are deaths and immigration, individuals exiting our population. So births plus immigration minus deaths minus immigrants uh, lead to changes in population size. So what we're going to do today is explore a little bit more about how populations grow, what limits their growth. Then you guys are going to do an activity, worksheet, homework assignment, whenever you get to do it, whenever you have time to do it. That's going to give you a little bit more practice in calculating growth rates and predicting growth rates, and think about why populations vary in their growth rates. So first, we're going to talk a bit about a case study. So let's go ahead and read this. So Thomas Austin, he was an Englishman who migrated to southern Australia to farm the land. Sounds like a great idea. His property, which is called Barwon Park, was located near Winchelsea, Victoria, Australia. In October of 1859, that was an important year, that's when Darwin published On the Origin of Species, homesick for his homeland and the hunting he used to enjoy way back in England, Thomas enlisted his nephew William Austin, who still resided in England, to send 24 wild English rabbits, which Thomas then released onto his land. Dun dun dun. Thomas dismissed the act as benign, not realizing the drastic consequences of his actions. You don't want to be this guy. Due to the well known prolific nature of rabbits, they breed like rabbits, and the suitability of the Australian climate, within 6 years, that population of 24 rabbits had increased to 22 million, 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 million. By the 1930s, Australia's rabbit populations were estimated to exceed 750 million. That's crazy. So, what I want you to think about now is how did the populations grow so large so quickly? Okay? And what might the consequences be on the local ecosystem? So, take a minute, pause, and think about this. Talk about it with your neighbor. How did the populations grow so large so quickly? And what might the consequences be on their local ecosystem there in Australia? Okay, I'm getting ready to move on. So pause if you haven't talked about it already. So why did the population grow so quickly? There are a number of reasons, but some things that you could have talked about were, first of all, the fact that they had few natural predators. There also weren't any natural diseases there. And this is really common in introduced species. When species are introduced into a new area, those that are really highly invasive are invasive because they are released from natural pressures that keep their population in check. Okay, so because they lacked predators, because there weren't any diseases that naturally afflicted them, they could grow almost unchecked. They also had abundant resources, lower competition. So these two environmental factors together could lead to sort of unchecked growth because you had so many births and fewer deaths. So the birth rate skyrocketed, death rates were relatively low, and they expanded into this new area and just blew up. So this type of unchecked growth, like we just talked about in these rabbits, is called exponential growth. So oftentimes you'll see a chart like this, a graph like this, and sometimes it's called a J curve. That's because it's shaped like a J. And so this exponential growth is basically unchecked. There's little predator, there are a few predators. There's abundant resources, and so the birth rates skyrocket, death rates are low, and so you get this really, really rapid growth rate. So another thing that we call this is the population's biotic potential. So you can think of that as the potential for growth with these limitations removed. Essentially, with limitations like predators, diseases, resource limitations, those have been removed. And so this is the population's biotic potential. This is also referred to as the intrinsic growth rate, and we denote this as R max. I told you a while ago that lots of things are called R. This has been done by different people in different disciplines, and it's annoying, but this is R max. This is the biotic potential, the exponential growth rate. So I want you guys to discuss now that we've considered this kind of extreme example, in what types of situations would we expect species to grow at their at their biotic potential? In what situations should they grow exponentially? So pause it now and take a minute to think about that and discuss. And I'm going to move on. So pause if you haven't discussed already. So hopefully you came up with some good ideas. There are lots of different reasons why this could take place. One is in the case of invasive species, like the rabbits that we just talked about. So in the top left there's a picture of some strawberry guava. It's an incredibly invasive tree here in Hawaii, and it has been introduced. It lacks predators. It lacks herbivores that beat it back. It has really high birth rates. The climate is favorable, so it just blows up. The bottom left, we've got a nice little island. So if you think about a population colonizing a new habitat where there are no competitors present, where there's abundant resources, in those situations you oftentimes see really rapid growth. And then also following extinctions. So following an extinction event like that which occurred when many of the dinosaurs went extinct, you could get sort of this explosion of population growth in species that are left behind as they kind of move and fill the niches that were vacated by the species that went extinct. So when we're calculating population growth, we can use this generic formula below to decide how many individuals would be added to each population. So we already said that R is our growth rate, and this is called the exponential growth equation. This represents growth under ideal conditions. So on the left side of this equation, you see delta n, so that's the change in population size over the change in time. You don't need to do any division here. This is just saying, how much is the population changing over a given period of time. And normally we consider that to be one generation. And that is equal to R, which is our exponential growth rate, our intrinsic rate of growth, times N, which is our current population size. So it's important to note that that equation, R times N, gives you the change in population over time, not the ending population size. So this will tell you how many individuals would be added to a population. So I want you to practice using exponential growth. So there's the equation on the left. I've given you two different scenarios with the same growth rate. And both of them have a different starting population size. So I want you to do three things. First, figure out how many are added to the population size, the starting population size for each of those. what is the ending population size after that one generation, assuming that there's no deaths? And then what is the per capita growth rate? To get at that, you would divide the growth by the starting population size. So the number of individuals that are added divided by the starting population size. So go ahead, pause, take a minute to calculate this out, and then I will give you the worked out equations in a moment. Okay, I'm going to keep going, so pause it if you haven't done this already. So here are those answers worked out. So for number 1, you just want to multiply r times n, 0.5 times 1,000 or 0.5 times 4,000, and that gives you the number of individuals added to the population, okay? So for number 2, what is the ending n? You would do r times n plus n, and that gives you the ending population size as you've added those 500 individuals to the starting population. For 3, what is the per capita growth rate? So this is growth divided by the starting n. And in both cases here, that is the same as our r. You'll see in a minute that that is not always the case. So here the per capita growth rate under exponential growth is just the same as that growth rate r. So in most situations, populations are not growing exponentially, at least not indefinitely. So I want you to think now, what factors can limit growth of a population? Take a minute, pause, think about what factors could limit the growth of a population. Okay, I'm about to move on. Pause it if you haven't discussed. Okay, hopefully you came up with some good answers, some good ideas. One is things like competition for resources. Okay, if you've got different species like this lion and hyena competing for resources, that could keep birth rates down, could drive up death rates. Top right there, we've got a disease. Okay, we've got cordyceps fungus. Remember that video we watched about cordyceps fungus and how as a population of insects increases, they become more likely to encounter their nemesis, and then that's going to drive them back. That'll keep them from growing exponentially. Limited space or other resources that limit population growth. We've got these penguins down there in the bottom left, which I'm hanging out with down in Antarctica right now. That limited space can keep populations growing exponentially. And then also encountering new predators or predators that are adapting to changes in your population can also drive growth rates down and increase death rates. So we don't always expect populations to grow exponentially. And for that, we have a nice little equation called the logistic growth equation that helps us account for density-dependent factors. Okay? And what I mean by density-dependent factors, this means as a population increases, competition for resources increases, so that's density dependent. Maybe disease outbreaks are density dependent. As individuals are becoming more closely packed, they're more likely to spread diseases, and that can drive up death rates. So all of those different factors can put a cap on the population size that can live in a given area at a given time. And we call that the carrying capacity. So on the left of this graph, you see the exponential growth. On the right, you see what logistic growth looks like, and it's this kind of S-shaped curve. So population might grow exponentially for a time, but then as competition increases, as these density-dependent factors increase, birth rates start to decline, death rate starts to increase, and they hit that carrying capacity and slow down dramatically. So the equation for this is over on the left, dn over dt, so that's our change in population size over time, is equal to r times n, which should look familiar, that's just our exponential growth, okay, times, and this is the key part right here, k minus n divided by k. So that's our carrying capacity minus the population size divided by our carrying capacity. So I want you to just think about what happens as we approach, mathematically, what happens as we approach the carrying capacity. As n becomes closer to k, that number in the parentheses becomes a really, really small fraction. So then what you're doing is you're multiplying a really small fraction by the biotic potential, which is that Rn. So that's the potential for growth under unlimited circumstances. So the closer you get to K, the more of a check that second part of the equation has on that first part of the equation. So we're going to work through a couple examples so you kind of see what I mean. So I want you to practice with each of these, with this new equation, practice running these numbers because you're going to have to do this on the exam. And I want you to understand this. So you've got R equals 0.5 in both scenarios. You've got a carrying capacity that's the same, but we've got a population size of 1,000 versus a population size of 4,000. So I want you to plug all this in, and I want you to calculate the same three things as we did before. How many are added, what's the ending n, and then most importantly, what the per capita growth rate is. And when you do that, I want you to think about what happens to that per capita growth rate as n approaches k. And remember that when we looked at r times n, that was just equal to our r. Our per capita growth rate was the same as that intrinsic growth rate. Here you're going to see something a little bit different, and I want you to think about what happens as it approaches k. All right, pause, take a few minutes, run these numbers, answer those questions. Okay, I'm moving on now. So I've just given you the calculations for the first one of these, but I want you to do both of them, talk about them together as a class, and see what happens. So for this first one, you would add, if you plug all these numbers in, you would add 400 to the population. So remember, before, under unchecked growth, we would add 500. So this part of the equation, that 500 times 0.8 is really important because that 0.8 is what's coming out of that parentheses, that second half of the equation. And so what we're doing is we're only getting 80%, we're only achieving 80% of the biotic potential when our population size is 1,000. And when that population size is 4,000, we're getting much less. We're actually only getting, so if you do that k minus n in the second part there, so we've got 5,000 minus 4,000 divided by 5,000. You're only getting 1,000 there divided by 5,000. So you're only going to be growing at a fifth of that biotic potential. So only 20% of the growth, which means you're not going to be adding very many. You're going to add a similar amount, but that per capita growth rate is very, very low, is much lower than when that population size is really small. And that's key. And that's that curve. That's that part of the curve as the population rate growth rate starts to slow down. That's slowing down because as you approach K, the per capita growth rate slows down dramatically because that competition is increasing, death rates are increasing, birth rates are decreasing, and that growth rate is going to slow to zero eventually. Sometimes the population will overshoot that carrying capacity and then crash and then settle back in near that carrying capacity. But that's the gist of it. That's the general idea. So in summary, to calculate the growth rate of a population, you need to take the difference between the ending and initial n and divide it by the initial n. And there's an example for you there. Another one, to determine n for the next generation, you've got to multiply n by r and then add that to n. And there's a shortcut which involves multiplying n by r plus 1, and that basically just takes into account that adding back the n into your population. And then for logistic growth, that carrying capacity is keeping us in check, keeping that population size in check. So what you guys are going to do now is you're going to work through a homework assignment, which you can start in class. In that homework assignment, you're going to practice calculating R. You're going to practice projecting growth rates into the future. You're going to practice doing that under logistic growth. You're going to think about what resources and what other environmental factors can influence growth rate, and hopefully get this all down really well so that you're ready for the test. And there's a video. I won't play it here because you won't be able to hear it, but I will have it. Make sure that, this link is available to you on that sheet, and I'll have Emery play this for you as well, so you guys can watch it as a class. And this is for number 5 on that worksheet. Okay, you're gonna do great. If you have any questions, ask Emery. You guys are awesome, and I miss you. And I hope you're doing really well. And best of luck on this assignment. And we'll see you next time.